Hey guys, so today we're going to cover the four-step method. This is used to solve nonlinear differential equations. A nonlinear differential equation can be seen in the example, which is basically just anything that is linear multiplied by another linear term will become nonlinear. So an example that we're going to solve later in this tutorial video is a population model. So this is dp dt is equal to kp 1 minus p. And this is nonlinear because there is a linear term, kp, multiplied by another linear term, 1 minus p. This can be solved using the four-step method. This is 1, separate, 2, integrate, 3, apply the conditions, and 4, sketch. These 4 steps can solve all kinds of nonlinear differential equations, such as different population models, mixing models, etc. So today we're going to take the example here, and we're going to apply the 4 steps to it. Alright, so to start we need to separate. This means we need to get the two variables, the dependent and the independent variables, on different sides of the equation. So in this case, we need to separate dp and dt. We do this by bringing dt onto the right-hand side and all p terms onto the left-hand side. So divide the right-hand side by divide both sides by kp times 1 minus p, and multiply the right-hand side by dt. And that's the first step. Now we're going to integrate. In order to integrate this, we need to do the cover-up method on the left-hand side. So the cover-up method separates this into two different fractions. We just have to solve the a and the b terms in order to separate them. This makes the integration a lot simpler for us. So in order to do this, what you do is, we're going to do the cover-up method for this one, and we're going to take this term here, and we're going to find whatever makes that term 0. So in this case, the only variable is p, so p would be 0, would make that whole term 0. And then you're going to cover up kp here, and you're going to put in 0 for p. That would give us 1. That means a is equal to 1. And then you're going to do the same thing for b, so whatever would make that term 0. So in this case, 1 for p would make that whole term 0. And then we're going to cover up 1 minus p and put in 1 for p. So that'll give us b is equal to 1 over k. So that just gives us our two fractions. So we have 1 over kp, 1 minus p, is equal to 1 over kp plus 1 over k, 1 minus p. So we're going to do the integration in two separate steps. We'll do the right-hand side first and then the left-hand side. So the right-hand side is the integral of dt. This is just equal to t. And then the left-hand side is equal to the integral of what we have above, so 1 over kp plus 1 over k, 1 minus p dp. Now in this case, we can bring the 1 over k in front because it's in both terms, and we're left with this. Now doing the integral of this, we get 1 over k multiplied by the ln of p minus the ln of 1 minus p. This is minus here because of the minus inside, right here. And then using our log rules, we can simplify this to 1 over k ln of p over 1 minus p. because the negative sign means that they can be divided. Now we're going to bring these two together, and this is our final answer for the integration part. So it's 1 over k ln of p over 1 minus p is equal to t. But we can't forget our integration constant, so that's the next step. So what I'm going to do is I'm going to multiply to get the k on the other side. kt, and then I'm going to add the constant. You don't have to multiply the constant by k because a constant times another constant is still a constant. So our third step is to apply the initial conditions. So in our case, the initial conditions are p is equal to p naught, t is equal to 0. So we're going to put those into the equation that we just solved for and solve for c. So we get the ln of p naught 1 minus p naught is equal to c, because the kt term gets canceled because t is 0. So we're going to put that into our final equation. Ln of p 1 minus p is equal to kt plus ln of p naught 1 minus p naught. Now the only problem with this is that we have to get it in terms of p, not the ln of p. So in order to do that, we're going to take the exponential of both sides. So this will become e to the ln of something becomes just the something. So that will be p1 minus p is equal to, and we're going to call all this just a variable just so it's easier for us to see. So we're just going to call that d. So that'll be e to the d, where d is equal to kt plus ln of p naught 1 minus p naught. And then we need to get p by itself, so we'll go p is equal to e to the d 1 minus p is equal to e to the d minus p e to the d, p plus p e to the d is equal to e to the d, and then we'll get as the final answer, where d is written up above. So now we just have one more step that we have to do, which is sketch. This is mostly done through logic. So first we're going to draw the dp dt graph. So this is going to look like this. Now there's two ways that we can do this. Some professors allow for graphing calculators, so you can use a graphing software for this, or you can do it based on logic, or you can put in values and go from there. I'm just going to show you what the graph looks like, and then I'll explain it at the end. So, as you can see here, this is the dp dt versus p graph. And it starts off at 0 because if the population can't grow if there's no population to begin with. And then as it increases, so does the population, and then as it decreases, it looks like that. Now, and then the other graph is P versus T, and since there's a 1 in the original equation up here, that is what P approaches. However, this depends on the value of P naught to begin with. So what is the population at the start of the model when T is equal to 0? And that depends on if it approaches 0 from the below or it approaches 0 from above. So this is how you do the 4-step method to solve nonlinear equations. You can use this for many different nonlinear models. I hope you guys enjoyed this video, and yeah, thank you for watching.